So today, before we start lesson 6.4, we're going to go over some bell work. I noticed that one of your homework problems from yesterday, there was a problem, a particular problem that looked very much like an exponential function, but was not. And as I was going around, several of you missed it. And that's okay, because it really has to do with a minute detail in our definition of exponential functions and that general form. So looking at this, it says determine whether or not the following equations represent linear or exponential functions. What is the first one? Is that a linear function or an exponential function? Linear. And what kind of line does that form?
Straight.
Well, what kind of straight line? Horizontal, right. So this is linear. So this is a linear function. It forms a horizontal line. And just as a reminder, what is my slope for that line? 0. Remember the skier example? My slope is 0. What's my y-intercept? 2. Number 2. Is number 2 exponential linear? What is it? Is it such a question? Neither. Why would it be neither? Yeah, because the 3 is negative, and according to our definition, whenever you wrote your notes the other day about y equals a b to the x, there were certain requirements that the form had to meet, and one of them was that b had to be greater than 0, and in this case, b is less than 0. It's a negative 3 actually, so it is not an exponential function. And the reason it's not an exponential function is because if we raise a negative by an even exponent, what will the result be? Positive or negative? If we raise it by an odd exponent, what will the result be? Negative. So actually it kind of bounces up and down, right? In our exponential functions, they're smooth curves either going up or going down. Does that make sense? So here, we have y equals negative 2 times 3x. What is that? That is exponential. So we can have a negative a value as long as our b is greater than 0. Okay. So we have a pretty complicated looking exponential function here, and we're told to describe the differences between this and its parent. First of all, what's the parent function? So f of x is equal to, is it negative 2 times 3 to the x or just 3 to the x?
3 to the x.
3 to the x, right. Okay, so 3 to the x. That's our parent. And everything around it is some sort of transformation. It's moving up and down, stretching or shrinking, that kind of thing. So what's the negative do? It reflects it, so we have a reflection. What does the 2 do? Stretch. It stretches it. Remember, if we have an a value greater than 1, it's a stretch. So it's stretching it by a factor of 2. Good. What does the plus 1 do? Yep. Horizontal translation. Remember those words, horizontal translation? Translation meaning movement. So horizontal translation. Left. And then what does a minus 5 do? Yeah, so that's a vertical translation, so movement up and down. So movement down 5 units. So a vertical translation 5 units down. Okay. you have any questions on that? Yes. It comes from this A value. Yeah, the A value is going to tell us a couple of things. It's going to tell us stretching or shrinking. What other crucial information does it tell us? The A value. The y-intercept. Right. It tells us the y-intercept as well. Great. Any other questions? It's all good. That was all good. Yes. The negative. So the y-intercept is made up of both the negative and the 2. Right, so if I were to graph this, I'd start with that 0, negative 2. And then, of course, I would multiply by 3 to get the next y value, multiply by 3, and then divide by 3 to get the one before it, right? We talked about that last time. And then that negative, that tells us the reflection, that tells us the stretch. And together, they form our y-intercept. Does that make sense? Okay, good. All right, we're going to start notes for section 6.4, and then we're going to do notes today, and tomorrow we'll do an activity of some sort. All right, so section 6.4 is about exponential growth and decay. Exponential growth and decay is something that you'll see continued throughout all of algebra. So it's very important because it allows us to see what happens to a given population after a certain set of circumstances. And we'll look at different scenarios with people and with bacteria and what happens over time. So as we can see here, the essential question are, what are some of the characteristics of exponential growth and decay functions? An exponential growth occurs when a quantity increases by the same factor over intervals of time. So we talked about 2 types of graphs that will increase. We have something going left to right and another going right to left. There's only one of these that fits the qualifications for an exponential growth. Do you think it's this first one or the second one? The first one, okay? Why would it be the first one and not the second one? Yes. Yeah, there's one particular variable that's decreasing that can't be decreasing. Our x values represent our time, right? And so over time, we have to be able to increase, right? Well, this is going back in time, isn't it? So as you're going back in time, it's increasing. But that doesn't fit the definition of an exponential growth. An exponential growth only occurs when a quantity increases by the same factor over equal intervals of time. So we're looking at a very specific exponential graph, and that's this one here. So we have a formula. And you might be thinking, well, do I get a note card? Because I don't know if I can remember this formula. You can remember this formula, and I'll show you why. It's actually just a variant of y equals a b to the x. And it says here in the study tip, it says, notice that an exponential growth function is of the form y equals a b to the x, where b is replaced by 1 plus r. So the only difference is, for a growth, you have 1 plus r replacing b, and then x is replaced with t, because t represents time. So the only difference is you're replacing this b with a 1 plus r and the x with the t. So don't overcomplicate it, okay? It says a function of the form y equals a, and then we replaced b with 1 plus r. To the t, we replaced x with t, where a is greater than 0. So like last time when we were talking about the definition of an exponential function in general, we have some stipulations, some little details here that are very important. A has to be greater than 0, because obviously if it was 0, we would just get 0. And if it was less than 0, we would get a negative, which is what we don't want. And r has to be greater than 0. This is extremely important, r being greater than 0. If r is greater than 0, will I ever have an amount less than 1 in the parentheses? No. So in the future, in a future couple of slides here, if you see something like this, you should know, because you see 1.08, that's greater than 1, this is a growth. Later on, we're going to have to determine whether or not, given equations, if those are growths or if they're decays. And it really just depends on what's inside that parentheses. So we have different representations for the variables in that equation. Y being the final amount after a set amount of time, and the growth rate being taken into account. A being the initial amount, so A being what we start with. So I could start with, for example, 3 bacteria, or 3 coins, or 3 people here. The rate of growth in decimal form, so my rate of growth is 1.08. Oh, sorry, just kidding. My rate of growth is just 0.08, right? It's just the R. My growth factor is 1.08. Time being T, of course. And it'll all make more sense when we see some examples. Do you have any questions about this basic formula? Yes?
So B equals the growth rate?
B equals the growth factor. Yeah, the growth factor. The rate of growth is just a percentage, it's just R, right? So you have a rate of growth, which is 0.08, so 8%. And then you have a growth factor, which is 1.08. Yeah? Okay. Let's look at a word problem. Okay. This says, the inaugural attendance of an annual music festival is 150,000 people. The attendance Y increases by 8% each year. So we want to know, basically, based on this, what's going to happen in the 5th year, 6th year, 7th year, etc. So the very first thing we have to do is model this situation using an exponential function. So it says, write an exponential growth function that represents the attendance after T years. So I'm going to remember my general formula. And the way I remember it is, I remember the general form for an exponential function, and I think to myself, how is this different? Well, the y stays the same, the a stays the same, the b is replaced with what? 1 plus r, my growth factor, and my x is replaced with t. Okay, so I already have the formula. So now I just have to plug some stuff in. A is my initial amount, so what's A going to be replaced with? Yeah, so the 150,000 that I start with. 1 plus R. What's the R? Yeah, 0.08. It needs to represent the 8%. And then I have my T. So all I have to do is just add 1 and 0.08, and I get Y equals 150,000 times the quantity 1.08 raised to the T. There I go. So I modeled that situation with an exponential function. Do you have any questions? It's really just a matter of, do you remember the formula? Can you plug in what you have? B says, how many people will attend the festival in the 5th year? Round your answer to the nearest 1,000. A couple things that you need to know. Most of the time with these questions, I'm going to tell you specifically how I want you to round. So if I want you to round to the nearest 1,000, not 1,000, then I want you to round to a 1,000 number, so like 2,034, okay? Now if I say 1,000, then of course we'll take into account decimals. So you want to make sure you double check and see how I want you to round your answer. The other thing you want to do and pay particular attention to is this 5th year. What most people will do is they'll say, well, oh, 5th year, so I'm going to replace T with 5. What's wrong with that? Why can't I replace T with 5? Well, T is time, right? So I do want to know what happened in the 5th year. Why will I have to use 4 instead of 5, even though it wants to know the 5th year? Guess what? Not quite. It has something to do with the first year. What is the first year? How do I represent the first year? Yes?
There's already 1.08, so the that happens already.
Yeah. Well, yes. Yes. So if I use 1 to represent the first year, what's going to happen to my initial population? The first year, it's going to take into account 1.08. So my first year didn't have 150,000 times 1.08. It just had 150,000. So how do I make this a 1? How do I make the 1.08t a 1? So it's just 150,000. I replace t with what? 0, right? So to represent the first year. So to represent the first year, I just want 150,000. I don't want anything else being multiplied by that 150,000. Does that make sense? Because in the first year, it's 150,000. That means that I cannot have this next to it. I cannot multiply by anything other than a 1. Well, I know anything to the 0th power is 1. So that means that t equaling 0 is the first year. If 0 is the first year, then t equaling 4 must be the 5th. Does that make sense before I actually complete the calculation? Okay? Okay. So, this is just a matter of correctly inputting it into your calculator. So, y equals 150,000 times 1.08 to the 4th. So you know you have to take into account order of operations. So you want to, in your calculator, do 1.08 to the 4th first, and then multiply it by 150,000. Because again, your calculator does not take into account order of operations for you. You have to know in advance what comes first. So once you do 1.08 and you raise it to the 4th, again, if you can't find the 4th as an exponent on your calculator, use that caret button. It's called a caret, that. So input that in your calculator, and then multiply that by 150,000 to get your answer. And your final amount after the 5th year should be, rounded to the nearest thousand, is 204,073 people. Include your units. Do you have any questions about that? Okay. Okay, if you're watching, make sure to pause this and try it. I'm going to show the answer now. So, for this particular problem, I should have gotten 1.15 to the t times 500,000 and about 1,160,000. Now, when you plugged everything into the calculator, when you did this, your t should have been raised to the what power? 5th or 6? Did you get this? Okay, so let's think about this. A website has 500,000 members in 2010. 2010, that's when t equals what? 2010 is when t equals 0. So that's in 2010. In 2011, that's when t equals 1. 2012, that's when t equals 2. 13, 14, 15, 16. Okay? So, don't just think it's going to be one away. You have to look at the first year, 2010, and then go up from there. So t should be 6. Now, when you plug this in your calculator, what you'll end up with is 1156,530.383. Okay. Now, looking at this, ones, tens, hundreds, thousands, 10,000s, right? So it says it wants you to round to the nearest 10,000. That's why they changed this. So you look again, ones, tens, hundreds, thousands, 10,000. And so you want to round this up to 1,160,000. Does that make sense? Yes.
We always use it for the
Well, to answer your question, it really, like I said, it depends on your initial year. So yes, time has to be represented in years, but more importantly, given your year, or given whatever you start with, you always start with 0. Because you're given an initial amount, and that initial amount can't be multiplied by anything here. So t will always be 0. That's what you have to start with. And then from there, just count up. 2010, 11, 12, 13, 14, 15, 16. Okay, does that make better sense? Again, pay attention to the rounding. And that would be members. They didn't do a very good job of labeling their units, but make sure that you do. Oh, I found this online. So if you're watching, we are now transitioning from growth to decay. So it says exponential decay occurs when a quantity decreases by the same factor over equal intervals of time. So we're going to first of all take a look at those two sketches that we examined in the previous slide. We said a growth went up from left to right. A decay will go up from right to left. Why is it that I can represent a decay with this second graph? Yes. Yeah, as I'm moving in time, what's happening to my values? They're decreasing, right? So two scenarios, growth, decay. Same thing. The only difference here is that instead of 1 plus r, what do we have? 1 minus r, which means that my decay factor will always be between 0 and 1, right? So 0.98, 0.75. So if I see something like this, y equals 3, and then you have, let's just say 0.98 raised to the t, then I know that that's a decay. It says a function, an exponential decay function is a function of the form y equals a times the quantity 1 minus r raised to the t where a is greater than 0. So a still has to be greater than 0. And r is between 0 and 1. So it's a decimal. That is less than 1, so 8%, 80%, etc., 0.8, 0.08. And that is an exponential decay function. Everything else is pretty much the same, except for 1 minus r as opposed to 1 plus r. Do you have any questions? All right, let's move on. So here we're looking at a chart and determining whether or not that chart demonstrates a growth or decay exponentially, or neither. So we know that x's are just going to continually go up by 1. So for example, the first year, second year, third year, fourth year, etc. So x represents time in this case. Y, we have to look at y. That's what we're going to examine to determine whether or not it's growth or decay. So what do you think? Is it growth, decay, or neither? Decay. Why is it decay? Yes. You're multiplying by what each time? 1/3, right? So you're dividing by 3. So 27 divided, or 270 divided by 3 is 90, divided by 3 is 30, divided by 3 is 10. So each time we're multiplying by 1/3. Which means that we have that growth factor that is in between 0 and 1. Does that make sense? Okay, the next one. Growth or decay? growth. What is your ratio that you're multiplying by? 2. So we have so we're doubling each year. So that's a growth. So we're doubling each year, that's what the graph will look like. We're going down each year, so that's what that graph will look like. Okay, questions? All right, we'll skip the next slide. That was practice. I think you got it. All right, our last example, we'll finish with this. It says determine whether each function represents exponential growth or exponential decay. Identify the percent rate of change. That percent rate of change is the R value. So in other words, what is my R value? So for A, it says y equals 5 times the quantity 1.07t. What do you think that is? Is that a growth or is that a decay? That's a growth. How do you know? Yeah, it's greater than 1. So that's, we already know it's a growth. How do you suppose we determine our R value? Any ideas? Yes. Yeah, exactly. So in other words, we just set 1 plus R equal to 1.07, right? That's our growth factor, and we just subtract 1. So what's our percent rate of change here? Yeah, and expressed as a percent, it'll be 7%. Does that make sense? What about the next one, growth or decay? Decay. How do you know? Less than 1. So what do we do in this case to find the value of R? Yeah, so, and we also need to remember that we have a negative, so we have to switch the sign as well. So we have 1 minus R equals 0.98. Then I subtract 1, or subtract it from 1 to make sure that I get a positive value. If I subtract 1 on both sides, I get negative R equals 0.02, and that's also negative, so R equals 0.02. So what's my percent rate of change here? 2%. So given my growth factor, can I find my rate? That's what you're trying to ask yourself. All right, that's it. Do you have any questions about this section? Tomorrow we're going to review prior to go take a quiz. You will not have any homework tomorrow other than to study for your quiz. Here is your updated table of contents. If you get done with this homework tonight, you will not have homework tomorrow.